The universe is vast, but what if I told you that somewhere out there, almost nothing exists at all? Not empty space filled with stars, not quiet cosmic dust, but an entire region so barren it could make the word void feel alive. This place is called the Boötes Void, stretching over 330 million light-years across. To put that in perspective, light itself, moving at 186,000 miles per second, would take 330 million years to cross it. It's not just a big empty space, it's almost nothingness made tangible in the cosmos. Imagine staring into the universe and finding a hole so large it swallows galaxies whole. That's where Boötes lives. Despite its enormous size, this void holds very few galaxies. Less than 60 have been detected inside it. Compare that to our Milky Way neighborhood, where galaxies cluster together like cities on a map. The emptiness here isn't just unusual, it's shocking. Scientists first stumbled upon it in 1981, and at the time, they couldn't believe what they were seeing. It was as if someone had scooped out a huge chunk of the universe and left nothing behind. But here's the truly eerie part. The Boötes Void isn't isolated. It's part of a larger cosmic web, a structure that binds galaxies together. Yet inside this web, the void is a gaping absence, a place where the rules of clustering seem to vanish. Now think about what that means on a human level. When we look up at the night sky, we see countless points of light, stars scattered like sparks of life. We are comforted by their presence, but the Boötes Void challenges that perception. It's not just far away, it's fundamentally different. It forces us to confront the idea of absolute emptiness. Could such nothingness exist elsewhere? Could there be more voids like this invisible to us, shaping the universe in ways we barely understand? Scientists believe the universe is a patchwork of dense clusters and vast voids, and yet the Boötes Void is one of the most extreme examples, almost unnervingly perfect in its emptiness. The Boötes Void is not just empty, it's a window into the large-scale structure of the universe. Galaxies are not sprinkled randomly through space, they form a cosmic web, a vast network of filaments, sheets, and clusters, leaving enormous voids between them. The Boötes Void is one of these gaps, but it is extreme, an anomaly in the cosmic web. Cosmologists call it a supervoid, a region of space where matter density drops to near zero compared to the average. Imagine taking the Milky Way, the Andromeda Galaxy, and dozens of neighboring galaxies and stretching them across a void the size of 1,000 Milky Ways. That is the scale of emptiness we are dealing with. How did it form? One leading theory involves the growth of the universe itself. After the Big Bang, the universe was nearly uniform, filled with tiny fluctuations in density. Gravity then amplified these fluctuations over billions of years. Dense regions attracted more matter, forming galaxies and clusters, while the less dense regions became emptier and emptier. The Boötes Void could be the result of such an underdense region expanding over cosmic time. Another possibility is that it formed from the merging of smaller voids, a cosmic coalescence, leaving behind one massive, nearly perfect emptiness. Either way, its existence challenges our understanding of how matter organizes itself on the grandest scales. Yet, when we look inside the void, there is still something there, albeit very little. Observations have found a handful of galaxies, mostly small and faint, lingering like lonely outposts in a desert. These galaxies are often unusual. Many are low-mass, star-forming galaxies that somehow survived in this harsh, isolated environment. Their isolation allows astronomers to study galaxy formation in near-perfect conditions, free from the gravitational chaos of clusters. It's like observing life on a deserted island in the middle of the ocean, revealing insights that crowded cities could never provide. Studies like Rojas et al. 2004 show that void galaxies often have different star formation rates and structures compared to galaxies in denser regions, hinting at the subtle ways environment shapes cosmic evolution. What makes the Boötes Void even more mysterious is its size and symmetry. At 330 million light-years across, it occupies almost 1% of the observable universe. That may sound small, but in cosmic terms, it is colossal. Its spherical shape is remarkable because voids formed from random fluctuations usually have irregular boundaries. This symmetry has led some theorists to speculate whether there could be unknown physical processes at work, perhaps even phenomena beyond the standard model of cosmology. Could dark energy, the mysterious force accelerating the universe's expansion, play a role in enlarging such voids? Or could primordial conditions in the early universe have created large-scale patterns we still fail to understand? Every discovery inside the Boötes Void is like peeking at a cosmic secret written in the language of gravity, time, and matter. But the implications of this emptiness go beyond astrophysics. They brush against philosophy and human perception. Humans have an inherent fear of emptiness, a psychological response to voids and isolation. The Boötes Void embodies that fear on a universal scale. When we study it, we confront not only the laws of physics, but also our own intuition about space, existence, and the significance of matter. It's an existential mirror. Looking into the void, we are forced to ask how much of the universe is truly there, and how much is a backdrop for the galaxies and stars we take for granted. To truly understand the Boötes Void, we need to explore how dark matter and the cosmic microwave background, CMB, shape the universe on these enormous scales. Galaxies form where dark matter, the invisible scaffolding of the cosmos, clumps together. The Boötes Void, by contrast, is a place where dark matter density is remarkably low. Imagine the cosmic web as a three-dimensional lattice of invisible threads. The filaments are highways along which matter travels, forming clusters and superclusters. The voids, like Boötes, are the vast spaces in between, regions where the threads are nearly absent. Without these threads, galaxies struggle to form, which explains why Boötes contains so few luminous bodies. Modern observations using the Sloan Digital Sky Survey, SDSS, have mapped the Boötes Void in unprecedented detail. These surveys reveal that the few galaxies present are not randomly scattered. They tend to lie along the edges, forming a thin, tenuous shell, as if the void is a hollow bubble suspended in space. This arrangement supports the theory that voids are expanding regions in an otherwise expanding universe. Think of cosmic inflation as stretching the fabric of space itself. As overdense regions pulled matter inward, underdense regions like Boötes expanded faster, leaving behind a near-empty cavity. Some simulations suggest that this process could continue for billions of years, eventually making the voids even emptier as the universe ages. The emptiness of Boötes also provides a natural laboratory for testing alternative cosmological models. For example, theories involving modified gravity or interactions between dark matter and dark energy predict subtle differences in how voids evolve. By comparing observations with simulations, astrophysicists can refine these models and potentially uncover new physics. One intriguing idea is that voids could reveal anisotropies in the expansion of the universe, tiny directional differences that might hint at deeper structures in spacetime itself. Observing how galaxies move inside and around Boötes allows scientists to measure the gravitational effects of both visible and invisible matter, offering a rare glimpse into the unseen architecture of the cosmos. Beyond structure formation, the Boötes Void challenges our perception of cosmic history. Light from the galaxies inside and around the void tells us a story stretching back billions of years. Observing these galaxies is like looking back in time, but instead of seeing densely packed clusters, we see almost nothing. This stark contrast allows astronomers to study galaxy evolution in isolation, free from the environmental pressures that dominate in clusters. Some galaxies in the void show unusually high star formation rates, while others appear dormant, as if their cosmic environment has dictated entirely different fates. In other words, Boötes is not merely empty, it is a place where the rules of galaxy life are rewritten by absence itself. One of the most powerful tools for understanding structures like the Boötes Void is the cosmic microwave background radiation, the faint afterglow of the Big Bang. This radiation, first detected in 1965 by Arno Penzias and Robert Wilson, is essentially a snapshot of the universe when it was only 380,000 years old. Modern missions like Planck have mapped this radiation with extraordinary precision, revealing tiny fluctuations in temperature, differences of only 1 part in 100,000. Those tiny fluctuations became today's galaxies, clusters, and voids. Now here is where the science becomes subtle. Large voids can leave imprints on the cosmic microwave background through something called the integrated Sachs-Wolf effect. As CMB photons travel across billions of light years, they pass through massive structures, clusters, superclusters, and voids. If a photon passes through a dense cluster, gravity slightly shifts its energy. If it passes through a void, the opposite happens. Because dark energy is accelerating cosmic expansion, voids grow while photons are crossing them. This changing gravitational landscape can cause slight temperature shifts in the background radiation. In theory, extremely large voids could create measurable cold spots in the CMB. This leads to a fascinating question. Could a structure like the Boötes Void influence what we see in the microwave sky?
Some researchers have studied connections between supervoids and anomalies such as the so-called CMB cold spot. While Boötes itself is not directly responsible for that specific anomaly, studies of supervoids show that these enormous underdensities do subtly affect background radiation measurements. This makes voids critical testing grounds for the standard cosmological model, the lambda CDM model, which describes a universe composed of dark energy, lambda, cold dark matter, and ordinary matter. If observations of void behavior ever significantly diverge from lambda CDM predictions, it would not be a small correction, it would be a foundational shift in cosmology. And that is why astronomers are now mapping voids with increasing precision. The Sloan Digital Sky Survey has cataloged hundreds of cosmic voids across billions of light years. Upcoming missions like Euclid and the Vera C. Rubin Observatory will push this mapping even further, constructing three-dimensional maps of the universe with tens of millions of galaxies. With that data, cosmologists will be able to measure void shapes, growth rates, and gravitational effects with unprecedented statistical power. Why does this matter? Because voids may be one of the cleanest environments to study dark energy. In dense regions, gravitational interactions are chaotic. Galaxies merge, collide, distort spacetime. But in voids, the gravitational field is simpler. There are fewer complicating interactions. This makes voids almost like controlled experiments on cosmic expansion. By observing how galaxies move along the edges of the Boötes Void, scientists can measure the rate at which space itself is stretching. In some simulations, void interiors expand faster than the cosmic average. Over trillions of years, this could make voids dominate the universe's large-scale structure even more than they do today. In the far future, distant galaxies beyond our local group will drift away, carried by dark energy, and observers might see a sky increasingly defined by emptiness. The Boötes Void, then, may not be an anomaly. It may be a preview. But there is another, even more radical line of thinking emerging in theoretical cosmology. Some researchers have proposed that extremely large voids could mimic the observational effects attributed to dark energy itself. If we happen to live near the center of a gigantic underdense region, cosmic expansion measurements might appear accelerated due to geometric effects rather than a true cosmological constant. While current data strongly supports dark energy as real, void-based alternative models continue to be explored mathematically. This shows something profound. The emptiest regions of the universe are not scientifically empty at all. They are mathematically dense with implications. Inside the Boötes Void, the near absence of matter creates a unique environment for the interplay between gravity and the quantum vacuum. Even where galaxies are scarce, space is not completely empty. Quantum field theory predicts that the vacuum is filled with fluctuating energy, virtual particles that appear and vanish within fractions of a second. In regions of extreme underdensity like Boötes, these vacuum fluctuations are effectively unshielded by matter, making the void a natural laboratory to probe subtle effects of quantum fields on cosmic scales. Some theorists speculate that the interplay between dark energy and quantum vacuum fluctuations could slightly accelerate the expansion of voids compared to surrounding space, hinting at a connection between the microscopic quantum world and the macroscopic cosmic web. The dynamics of the void also challenge our understanding of cosmic entropy. In dense clusters, interactions among galaxies, collisions, mergers, and tidal distortions increase gravitational entropy over time. But in a void, these processes are minimal. Without complex gravitational interactions, the interior of the Boötes Void represents a region where the universe's evolution proceeds along a simpler, almost pristine trajectory. It's a region where the thermodynamic arrow of time is less chaotic, more uniform, offering a counterpoint to the disorder seen in galaxy clusters. By studying such regions, cosmologists can test fundamental assumptions about how entropy and structure formation operate across different cosmic environments. Observationally, astronomers are now able to measure subtle motions of galaxies along the void's boundaries, using redshift surveys and high-precision spectroscopy. These galaxies act like test particles in a gravitational experiment spanning hundreds of millions of light-years. Their velocities reveal not only the mass distribution of the void's interior, but also the expansion rate of space within and around it. Simulations suggest that void interiors expand faster than the surrounding universe, a phenomenon known as void differential expansion. Over billions of years, this could create a feedback loop, gradually enlarging voids while clusters grow more isolated, amplifying the contrast between dense and empty regions. Beyond physical measurements, the Boötes Void pushes theorists into speculative but rigorous territory. If we consider general relativity, empty regions of space still contribute to the overall curvature of spacetime. The absence of matter doesn't mean the void is flat. It simply changes the way gravitational waves propagate and how light bends across vast distances. Photons traveling through the void can experience subtle lensing effects, leading to minute distortions in our observations of the cosmic microwave background and distant galaxies. In this sense, the void acts as both a mirror and a lens, reflecting the underlying geometry of the universe while refracting our perception of its contents. There is also a growing interest in connecting voids to cosmic inflation. The inflationary epoch, an incredibly brief period right after the Big Bang, caused space itself to expand exponentially. Tiny quantum fluctuations during this epoch seeded the large-scale structures we see today. Voids like Boötes may preserve memory of these primordial fluctuations in a cleaner form than dense regions, which have undergone billions of years of nonlinear interactions. By analyzing void statistics, their size, shape, and distribution, cosmologists can test inflationary models, constraining parameters such as the spectrum of initial fluctuations and the nature of primordial density variations.
In addition, the Boötes Void serves as a counterpoint in the study of dark matter clustering. While dense regions reveal the gravitational pull of dark matter through galaxy motions, voids reveal its absence. The near-empty interiors confirm that dark matter is not uniform. It clusters where normal matter clusters, and leaves behind low-density regions where both ordinary and dark matter are scarce. Comparing simulations with observations allows scientists to refine the properties of dark matter particles, their interaction cross-section, distribution, and possible non-gravitational effects. In this way, the void is not just empty space, but a critical checkpoint in our understanding of the invisible framework holding the universe together. As the universe continues to expand under the influence of dark energy, voids like Boötes are expected to grow faster than the average cosmic expansion. This differential expansion has intriguing consequences. Over trillions of years, voids may dominate the volume of the universe, leaving galaxies and clusters isolated in ever smaller pockets of space. Simulations show that as matter flows from underdense regions into denser filaments, the contrast between voids and clusters intensifies. In essence, the universe could gradually evolve into a patchwork of nearly empty regions interspersed with a few densely packed cosmic islands. Boötes offers a real-time glimpse of this future in action, a cosmic preview of what vast emptiness can look like when stretched across hundreds of millions of light-years. Multiple supervoids, when considered together, could have collective effects on cosmic structure. Their gravitational influence subtly alters the motion of galaxies and the propagation of light across the universe. The interactions between voids may even contribute to large-scale anisotropies, tiny directional differences in the cosmic microwave background. Some researchers propose that by mapping supervoids like Boötes in 3 dimensions, we can reconstruct the dynamic evolution of the cosmic web, understanding not only where matter is today, but how it moved and expanded over billions of years. In other words, voids are not empty spectators, they actively participate in shaping the universe's large-scale architecture. The Boötes Void also raises fundamental questions about the ultimate fate of structure in the universe. If voids expand indefinitely, galaxies within or near them may eventually drift so far apart that communication, via light or any other signal, becomes impossible. From the perspective of a far future observer, the universe could appear almost completely empty, with only remnants of the local supercluster visible. In this sense, Boötes is both a laboratory and a warning. It illustrates how the universe's grand design can evolve toward isolation, offering clues to the long-term thermodynamic destiny of cosmic structures. The philosophical implications are equally compelling. Observing Boötes forces us to confront the scale of cosmic emptiness relative to human existence. Even the largest clusters of galaxies, the Milky Way or our nearest neighbors, seem insignificant when placed against a void stretching 330 million light-years. This stark emptiness highlights the fragility of cosmic structures and the remarkable circumstances that allow life to arise on a small planet within a relatively dense cluster of galaxies. In a universe dominated by voids, the very existence of stars, planets, and consciousness becomes a delicate anomaly in a backdrop of nothingness. From a scientific standpoint, Boötes also challenges our cosmological models. While lambda CDM remains the standard framework, the presence of extreme supervoids tests the limits of statistical predictions. If voids larger than Boötes were found, or if their shapes or expansion rates deviated significantly from predictions, it could signal new physics, perhaps a different form of dark energy, unknown interactions in dark matter, or subtle curvature effects in spacetime. Each measurement of a galaxy within or around Boötes becomes a critical data point, a probe into the very laws governing the cosmos. Finally, ongoing and future surveys promise to reveal even more about these enigmatic regions. The Euclid and the Vera Rubin Observatory will map billions of galaxies with exquisite precision. By cataloging voids, measuring their expansion, and observing how galaxies behave along their edges, astronomers hope to unlock deep insights into dark energy, cosmic inflation, and the ultimate large-scale fate of the universe. The Boötes Void, enormous yet sparse, continues to act as both a cosmic laboratory and a mirror, reflecting our deepest questions about existence, emptiness, and the nature of reality itself.
Inside the Boötes Void, the scarcity of matter leads to an environment where thermodynamics behaves unusually on cosmic scales. In dense galaxy clusters, gravitational interactions, collisions, and mergers increase the system's overall entropy. Heat, energy, and chaotic motion dominate. But in the near-empty void, entropy growth is much slower. Galaxies on the edges of the void move along predictable trajectories, minimally disturbed by neighboring structures. From a thermodynamic perspective, the Boötes Void represents a kind of cosmic low-entropy pocket, a region of relative order amidst the chaotic universe. This allows theorists to test fundamental assumptions about entropy and cosmic evolution, exploring questions like how large-scale structure contributes to the arrow of time itself. Beyond classical physics, the Boötes Void is a natural laboratory for quantum vacuum effects. Even where matter is sparse, the vacuum is never truly empty. Quantum fluctuations continuously generate virtual particles that pop in and out of existence, creating tiny, pervasive energy fields. In dense regions, these effects are largely masked by gravitational interactions. In Boötes, however, the absence of mass allows these vacuum phenomena to operate unimpeded. Some researchers suggest that this could subtly influence local expansion rates, or even act as a small-scale probe for interactions between dark energy and the quantum vacuum. In essence, the void offers a glimpse of how quantum processes ripple across the largest scales of space. The implications for cosmic evolution and the ultimate fate of the universe are profound. As voids expand, the surrounding filaments and clusters are pulled apart, increasing the isolation of cosmic structures. Over tens or hundreds of billions of years, galaxies within voids like Boötes could become effectively disconnected from the rest of the universe. Observers in these regions might see an increasingly empty sky, with few stars and no neighboring galaxies. This scenario illustrates a universe slowly evolving toward vast emptiness, dominated not by what exists, but by what does not. Boötes is a preview of that far future emptiness, a natural laboratory to study how cosmic expansion and dark energy sculpt the ultimate structure of reality.
Speculative cosmology pushes this even further. Some theorists have considered whether extremely large voids could mimic or amplify the effects attributed to dark energy, influencing observations of cosmic acceleration. While mainstream science supports a genuine cosmological constant, studying voids offers a way to test the boundaries of this assumption. Similarly, models of multiverse interactions suggest that the largest voids could arise from subtle shifts in the distribution of energy and matter across multiple universes. While highly theoretical, such ideas underscore how a seemingly empty space like Boötes can challenge and expand our understanding of physics, potentially connecting the vast scales of the cosmos with the most fundamental laws of nature. Finally, the Boötes Void challenges our human perception of scale and existence. On one hand, it is a purely scientific phenomenon, a measurable underdensity in the cosmic web. On the other hand, its sheer emptiness evokes an existential reflection. How much of the universe is defined by presence, and how much by absence? The void illustrates that emptiness is not just a philosophical concept, it is a measurable physical reality that shapes the cosmos. It acts as both a mirror and a window, showing us the limits of matter, the boundaries of observation, and the profound emptiness that lies at the heart of existence. One of the most subtle yet profound effects of enormous voids like Boötes is their influence on gravitational waves, the ripples in space-time predicted by Einstein and first observed directly in 2015 by LIGO scientific collaboration. Gravitational waves travel at the speed of light, but their propagation can be minutely affected by the large-scale distribution of matter. In a dense cluster, gravitational waves are slightly warped, delayed, or focused. Inside a void, however, the scarcity of matter allows these waves to travel with minimal interference, potentially preserving the original waveform over immense distances. By comparing signals traveling through voids and through denser regions, scientists can test models of space-time curvature and even probe the properties of dark matter and dark energy with extraordinary precision. Large voids also contribute to anisotropies in the universe. Even though the cosmos appears isotropic on average, tiny directional differences exist, slight variations in the cosmic microwave background, galaxy distributions, and large-scale flows. Voids like Boötes exaggerate these differences locally. Their expansion subtly affects the motion of nearby galaxies, creating bulk flows that ripple across millions of light-years. By studying these flows, cosmologists can reconstruct the evolution of the cosmic web, identifying how matter migrated from underdense regions to filaments and clusters. Essentially, Boötes acts like a gravitational fingerprint, encoding the history of structure formation in a region almost completely defined by what is not there. Looking even further ahead, the Boötes Void provides a window into the far future evolution of the universe. As dark energy continues to accelerate cosmic expansion, voids are expected to expand faster than average. This process could eventually isolate galaxy clusters and superclusters, leaving vast, nearly empty regions dominating the universe's volume. Galaxies along void edges might drift so far apart that they become cosmologically invisible to one another. From the perspective of a hypothetical far future observer within or near Boötes, the observable universe could appear almost entirely empty, with only remnants of local structures visible as faint, distant specks. In this sense, Boötes is not merely a curiosity, it is a preview of the universe's distant future, a tangible glimpse of cosmic isolation on an unimaginable scale. Some theorists even speculate about the ultimate thermodynamic fate of voids. While dense regions increase in entropy through complex gravitational interactions, voids' interiors evolve more slowly. Over trillions of years, as stars exhaust their fuel and black holes dominate, voids may act as reservoirs of low-entropy space, relatively untouched by chaotic processes elsewhere. Quantum effects, vacuum fluctuations, and dark energy interactions could continue to shape these regions in subtle ways, long after the death of most luminous structures. In other words, emptiness itself may persist far longer than anything else in the universe, suggesting that voids are not empty in a trivial sense, but are persistent, dynamic entities that carry the memory of cosmic evolution across billions of years. Across 330 million light-years, the Boötes Void stands as one of the clearest demonstrations that the universe is structured less like a solid object and more like a delicate web stretched across vast expanses of near-nothingness. Dense clusters are the exception. Emptiness is the rule. And in studying that rule, measuring galaxy motions along its boundary, mapping its gravitational imprint, testing it against simulations, and probing it with next-generation observatories, we are not merely cataloging absence, we are using the quietest regions of the universe to interrogate its loudest questions: how structure emerges, how space-time evolves, how energy shapes expansion, and how the cosmos ultimately approaches its asymptotic future. At the foundation lies perturbation theory applied to the early universe. After the Big Bang, matter density variations were incredibly small, about 1 part in 100,000, as seen in the cosmic microwave background. These fluctuations evolved under gravity according to equations derived from general relativity and fluid dynamics. In overdense regions, gravitational collapse amplified structure formation. In underdense regions, the opposite occurred. Matter flowed outward. Mathematically, this is described through the growth factor in cosmology, which determines how density contrasts evolve with time. In void regions, the density contrast becomes increasingly negative, meaning the matter density drops further below the cosmic mean as expansion continues. Nonlinear evolution complicates the picture. Early on, density fluctuations can be approximated linearly, but once contrasts grow large, simulations must incorporate full n-body gravitational calculations. These simulations track billions of particles representing dark matter evolving under mutual gravity. When researchers run such simulations within the lambda CDM framework, structures resembling Boötes naturally emerge, though extremely large voids sit at the statistical tail of the distribution. This statistical rarity is important. It means Boötes tests the extreme predictions of cosmological models rather than their average behavior. Inside these simulations, voids exhibit characteristic density profiles. The interior density drops to perhaps 10% of the cosmic mean or lower, then rises sharply at the boundary where galaxies accumulate. This boundary region is sometimes called a compensation wall, where displaced matter gathers. Observations of the Boötes void suggest a similar structure, a relatively sharp transition between near emptiness and filamentary clustering. The precise steepness of that transition can constrain dark matter properties. For instance, warm dark matter models predict slightly different small-scale structure compared to cold dark matter, potentially affecting how sharply void edges form. Void dynamics are also described using the Zeldovich approximation, a mathematical model for gravitational collapse and expansion. In this framework, underdense regions expand anisotropically along principal axes, sometimes becoming elongated rather than perfectly spherical. The near-spherical symmetry of Boötes therefore draws attention. Either its initial fluctuation was unusually symmetric, or non-linear merging of smaller voids smoothed its geometry over time. Statistical studies of void electicity help refine these interpretations.
Beyond gravity alone, baryonic physics, the behavior of ordinary matter, also plays a role. Gas dynamics, radiative cooling, and feedback from supernovae can subtly influence the few galaxies that inhabit void interiors. Because interactions are rare, these galaxies evolve differently from cluster galaxies. Their rotation curves, star formation histories, and metallicity distributions become sensitive probes of galaxy formation in isolation. In effect, void galaxies allow astronomers to separate internal evolutionary processes from environmental effects. Another mathematical frontier involves redshift space distortions. When we measure galaxy distances, we rely on redshift, the stretching of light due to cosmic expansion. However, galaxies also have peculiar velocities caused by gravitational attraction or repulsion. In void regions, galaxies tend to flow outward from the center toward denser edges. This creates measurable distortions in redshift maps. By modeling these distortions precisely, cosmologists can estimate the growth rate of structure, providing independent tests of general relativity on cosmic scales.
There is also increasing interest in using voids as probes of modified gravity theories. Some alternatives to general relativity predict enhanced gravitational forces in low-density environments, an effect known as fifth force screening. In dense clusters, such forces may be suppressed, but in voids they could become detectable. Measuring galaxy motions within Boötes could therefore test whether gravity behaves exactly as Einstein predicted or deviates slightly under extreme underdensity. As observational datasets grow, void catalogs are being analyzed statistically. Parameters such as void abundance, size distribution, clustering properties, and evolution with redshift are compared against cosmological simulations. The abundance of extremely large voids like Boötes constrains the amplitude of primordial density fluctuations, often parameterized as sigma 8 in cosmology. A mismatch between predicted and observed void statistics would signal tension in the standard cosmological model. Now consider the far future evolution of a void mathematically. In an accelerating universe dominated by dark energy, the scale factor grows exponentially. Underdense regions expand even more rapidly relative to dense ones. Over trillions of years, matter drains from void interiors almost completely, leaving behind ultra-isolated dark matter halos and faint stellar remnants. Radiation redshifts to longer wavelengths, approaching thermal equilibrium with the quantum vacuum. Entropy increases globally, yet locally within void interiors, structural complexity decreases toward near uniformity. From a geometric standpoint, the universe asymptotically approaches a de Sitter spacetime, a solution to Einstein's equations characterized by exponential expansion. In such a spacetime, horizons form. Beyond these horizons, information is permanently inaccessible. Voids become dominant not only volumetrically but observationally. They define the experiential universe of any future observer. The Boötes void, therefore, sits at the intersection of observation, simulation, and theory. It is not merely an empty patch, it is an extreme data point that sharpens cosmological parameters, tests gravity, probes dark matter properties, constrains inflationary initial conditions, and anticipates the thermodynamic destiny of structure. And yet, despite the precision of equations and simulations, something remains striking. From a distance of hundreds of millions of light-years, there exists a region where galaxies are scarce, light is sparse, and matter thins almost to nothing. The mathematics explains how it forms. The simulations reproduce it statistically. The observations confirm its structure. But its scale continues to challenge intuition. In cosmology, large-scale structure formation begins with the Friedmann equations, derived from Einstein's field equations under the assumption of large-scale homogeneity and isotropy. These equations describe how the cosmic scale factor, A of t, evolves with time depending on the energy content of the universe, matter, radiation, and dark energy. But voids are, by definition, deviations from homogeneity. To model them, cosmologists introduce density perturbations on top of the background expansion. Define the density contrast. Delta equals rho minus rho bar over rho bar, where rho is the local matter density and rho bar is the cosmic mean density. In overdense regions, delta is greater than 0. In voids, delta is less than 0. For small perturbations, linear theory predicts the density contrasts evolve proportionally to a growth factor d of t, but voids quickly enter the nonlinear regime because matter flows outward from their centers. The governing equation resembles a reversed collapse. Instead of contracting under gravity, the region expands faster than the background expansion. One elegant analytical model is the spherical expansion model, essentially the inverse of the spherical collapse model used for clusters. In this approximation, an underdense spherical region evolves according to a modified Friedmann equation with reduced matter density. Because gravity is weaker inside the void, the effective expansion rate is higher. Over time, this differential expansion increases the void's radius relative to the surrounding universe. For a sufficiently underdense initial perturbation, shell crossing occurs. Matter streams outward and accumulates at the boundary, forming a density ridge, the compensation wall observed in simulations. This is precisely what we expect in something like the Boötes Void, a low-density interior with a sharper transition at its edge. But real voids are not perfectly spherical. Their evolution is better described by the Zeldovich approximation, where particle trajectories follow x of q of t equals q plus d of t del phi of q. Here, q represents initial positions, d of t is the growth factor, and phi is the gravitational potential. In underdense regions, the displacement field causes particles to diverge rather than converge. Expansion proceeds along principal axes determined by the initial tidal field. This explains why many voids are elliptical or irregular. Yet the Boötes void appears unusually symmetric for its scale. This raises statistical questions. In Gaussian random field theory, which describes primordial fluctuations, extreme symmetric underdensities are rare but not impossible. Their probability depends sensitively on the amplitude of initial fluctuations. Therefore, accurately measuring the abundance of supervoids constrains early universe parameters such as the spectral index n sub s and fluctuation amplitude sigma sub 8. Now introduce dark energy. When the cosmological constant dominates, the background expansion accelerates, but underdense regions respond more dramatically because their local gravitational deceleration is weaker. In effect, dark energy amplifies void growth. In a matter-dominated universe, void expansion slows over time. In a dark energy-dominated universe, it accelerates. Thus, void size evolution becomes a probe of dark energy's equation of state parameter W. If W equals -1, dark energy behaves as a true cosmological constant. If W does not equal -1, void growth rates shift measurably. This is why next-generation surveys aim to measure void statistics with precision. Slight deviations in void expansion could reveal whether dark energy is dynamic rather than constant. Now consider modified gravity theories, such as scalar tensor models. Many of these predict screening mechanisms. Gravity behaves normally in dense environments, but is altered in low-density regions. Voids are precisely where such deviations would become most apparent. Galaxy velocities in the Boötes void could, in principle, detect enhanced gravitational forces if they exist. Mathematically, this involves modifying the Poisson equation governing gravitational potential. Del squared phi equals 4 pi g rho, arrow del squared phi equals 4 pi g effective rho, where g effective may vary depending on local density. In low-density environments, g effective could differ slightly from Newton's constant g. Precision mapping of galaxy flows around supervoids tests whether such modifications occur. Now extend this even further to the geometry of spacetime. In an accelerating universe approaching de Sitter space, the metric tends toward exponential expansion, AT proportional to EHT, where h becomes nearly constant. Inside vast voids, local curvature approaches that of empty de Sitter space more closely than in dense regions. Over immense timescales, void interiors become nearly pure dark energy-dominated spacetime. Matter density becomes negligible, gravitational interactions fade, structure thins toward uniformity. In that asymptotic regime, horizons dominate physics. Events beyond a certain radius can never influence a given observer. Information effectively disappears behind cosmological horizons. Voids, expanding faster than average, reach this isolation earlier. From a purely mathematical standpoint, the universe's late-time attractor solution is emptiness. Not absolute nothingness, but exponentially expanding, nearly matter-free spacetime. The Boötes void is a partial realization of that attractor already in progress. And here is the striking realization. What we call structure, galaxies, stars, clusters, occupies only a tiny fraction of cosmic volume. The dominant geometry of the universe is underdensity. The equations of cosmology do not predict a universe filled uniformly with galaxies. They predict a web stretched across expanding voids. The Boötes void is not a mistake in the structure. It is a confirmation of the mathematics. There is one more frontier where the Boötes void becomes profoundly important: precision cosmology through weak gravitational lensing. Even though the void contains very little matter, its absence of mass alters the path of light in a measurable way. When light from distant galaxies passes through or near a supervoid, the reduced gravitational potential slightly changes its trajectory and energy. This effect, sometimes called weak anti-lensing, causes tiny distortions in galaxy shapes and brightness. By statistically measuring these distortions across millions of background galaxies, cosmologists can reconstruct the mass deficit inside voids with remarkable accuracy. Unlike clusters, which create strong and dramatic lensing arcs, void lensing is subtle, almost whisper-like. But precisely because it is subtle, it becomes an exceptionally clean probe of large-scale structure. Measuring lensing around supervoids tests whether gravity behaves linearly at these scales, and whether dark matter truly follows the distribution predicted by cold dark matter models. Upcoming surveys from the Vera C. Rubin Observatory and Euclid will map billions of galaxies, allowing void lensing signals to be stacked and amplified statistically. For the first time, astronomers will measure not just where matter exists, but where it almost doesn't, turning absence into a measurable physical quantity. Another dimension lies in cosmic time evolution. When we observe the Boötes Void, we are not seeing it as it is now. Light from its galaxies has traveled hundreds of millions of years to reach us. By surveying voids at different redshifts, effectively looking at different epochs, scientists can track how void sizes and densities evolve. This allows direct comparison between theory and observation across billions of years. If voids grow exactly as predicted by lambda CDM cosmology, the growth rate will follow a specific curve tied to the expansion history of the universe. If discrepancies appear, they could indicate evolving dark energy or new gravitational physics. In this way, Boötes is not frozen in time. It is part of a dynamic sequence stretching from the early universe to the far future.
Step back now and consider the full arc. From tiny quantum fluctuations in the first fraction of a second after the Big Bang, to density contrasts imprinted in the cosmic microwave background, to gravitational evolution shaping filaments and clusters, to matter draining outward, forming a vast, nearly spherical emptiness, the Boötes Void is the result of every major force in cosmology working together over 13.8 billion years. General relativity governs its expansion. Dark matter sculpts its boundaries. Dark energy accelerates its growth. Quantum fluctuations seeded its origin. Observations measure its structure. Simulations reproduce it statistically. And yet, despite all that mathematical precision, what confronts us is staggering in its simplicity. A region 330 million light-years across containing almost nothing at all. The universe at its largest scales is not packed with galaxies. It is dominated by voids. Structure is rare. Emptiness is common. The Boötes Void is one of the clearest demonstrations of that truth, not a flaw in the cosmic design, but a natural consequence of its governing laws. If you found this journey into the deepest emptiness of the universe meaningful, if exploring how physics, gravity, and time create something so vast and so empty expanded your sense of reality, then subscribe to The Wandering Neuron. Because sometimes understanding the universe begins not with what is there, but with what isn't.